Hi, I'm Conor Houghton. This is lecture 17, the last lecture in the probability and combinatorics section of our unit Mathematics for Computer Science A. In this lecture, I'll be talking about the Gaussian distribution. So we already learned about the probability for continuous distributions. We learned that there's a probability density, P of x, and that if you integrate the probability density x1 to x2 of x, well, that gives the probability of x being in x1 to x2. So it gives the probability of that event, as it were. We saw that this was a density. It's just like the density of a material. Any given point in the material, infinitely small, has no mass, but it has a density. If you integrate the density, that gives you the mass for that region. Similarly here, an individual value of x will have zero probability of occurring, but it will have a density, and if you integrate the density over some region, in this case the interval x1 to x2, that will give you the probability inside that region. Now we only looked at one probability distribution so far, a continuous probability distribution, and that was the uniform distribution. We now are going to look at the most common probability distribution, or the most important probability distribution, the one that arises most often, which is the Gauss distribution, or the Gaussian distribution. And that has probability density given by P of x is equal to, and the business part is here, e to the x minus mu squared divided by 2 sigma squared, and then you have a normalization, which is 1 over the square root of 2 pi sigma squared. So that's the Gaussian distribution. I'll just write that down. It's the Gaussian distribution, or sometimes it's written as the Gaussian distribution. This bead-like shape here, a bit like a beta or a B, is a German letter whose equivalent in other alphabets is a double S. So this is the Gaussian distribution. It's shaped like this. So this is a Gaussian distribution with mu equals to 0 and sigma equals 1. We'll demonstrate that mu actually gives the mean, so we'll calculate the mean of this distribution. This is what it looks like. You can see it has this classic bell-shaped curve. It's often called a bell curve. It's also called a normal distribution. The reason it's so important is that, well, many processes that are the mixture of other processes. So if you have something that happens as a consequence of several different variables being added, there is a theorem which we're not going to discuss in this course, but there's a theorem that tells you, roughly speaking, that the sum of those different random variables will start to look like a Gaussian. And so, for example, noise. If you have a signal and it has some sort of distortion, that distortion is often described by a Gaussian distribution. Secondly, there are lots of other distributions that look somewhat like the normal distribution. So there are lots of random processes. When you make an effort to describe them, you end up with a continuous distribution, and it has a similar shape to this. And so often, to some approximation, it's useful to approximate that distribution with the Gaussian, and that's because the Gaussian actually has some nice properties. If you add two random variables that are Gaussian, that sum will also be Gaussian distribution, for example. So the Gaussian distribution is useful both because it often describes processes like the processes that produce noise. There are lots of things that are Gaussian distributed, and even those things that aren't Gaussian distributed, sometimes it's useful to approximate them with a Gaussian distribution. And so if you have some random variable p that is x that's described by a Gaussian distribution like this. In other words, if we have x such that the probability distribution for x is p of x, where p of x has this normal form, well then we would often write x twiddle means is described by, and then you would write this calligraphic end figure for normal distribution, and then you'd put in mu and sigma squared, or sometimes sigma. That's one of the bad parts about this notation. Sometimes people put sigma squared there, sometimes they put sigma there. And similarly, if x goes like n with 0 mean and unit variance, that's often called a standard normal distribution. and sometimes people even just call that the normal distribution. So what we have here is an example of a continuous distribution. As I said, it arises quite often, and it has this particular form. You might query the normalization. So one of the properties, of course, a distribution has to have is that the integral from minus infinity to infinity, p of x dx is equal to 1. That's assuming that the support is over minus infinity to infinity, as it is in this case. And so that tells us that for the normal distribution to make sense, we should have that the 1 over 2 pi sigma squared integral from minus infinity to infinity e to the minus x minus mu squared over 2 sigma squared dx. That should hold. And indeed, that does hold. We're not going to verify this calculation here. There's a very elegant trick for doing this integral. If you're interested in like elegant tricks or integrals, you could look that up. But it's slightly outside of the scope of this course. But basically that's telling us that 2 pi sigma squared is equal to the integral from minus infinity to infinity e to the minus x minus mu squared over 2 sigma x dx. And as it must be for this to make sense as a probability distribution. We'll use this formula now in the usual way to work out the mean. Obviously this would be terrible notation if the mean didn't work out to be mu, but we do need to check that. We can't just use the fact that that's the notation to tell us that the mean is mu. So what we're after, as usual, is the expected value of x. We have 1 is equal to 1 over the square root of 2 pi sigma squared minus infinity to infinity e to the minus x minus mu squared over 2 sigma squared dx. I'm going to differentiate in the usual way with respect to one of the parameters. Parameter I'll differentiate with respect to is mu, and so I'll get 0 is equal to 1 over 2 pi sigma squared. It's not affected by the differentiation. Minus infinity to infinity dd the mu of e to the minus over 2 sigma squared dx. And I'm going to use the chain rule to do this differentiation. So let me write it as dd mu of e to the what we call this w will be d e to the w dw dw d mu by the chain rule. The defining characteristic of the exponential is that when you differentiate it, you get yourself back, and so what we need here is the d mu of w. And in our case, the w is standing for everything up here, the exponent, so w would be equal to minus x minus mu squared over 2 sigma squared. So dw d mu will be equal to minus 2 x minus mu all over 2 sigma squared, cancel the 2's, and so we get that dd mu of e to the minus x minus mu squared over 2 sigma squared is equal to x minus mu over sigma squared of e to the minus x minus mu squared over 2 sigma squared. So if I put that back into here, I'll just copy it across. So what I wanted was, what I had was 0 is equal to 1 over square root of 2 pi sigma squared integral minus infinity to infinity dd mu of e to the minus x minus mu squared over 2 sigma squared dx, and that's equal to 1 over 2 pi sigma squared integral minus infinity to infinity, and there's an extra minus coming in, x minus mu over sigma squared e to the minus x minus mu squared over 2 sigma squared dx, multiply across by the sigma squared, and just sigma by 0 is 0, and then we might as well get rid of this plus as well, so we get 1 over 2 pi sigma squared minus infinity to infinity x minus mu e to the minus x minus mu squared all over 2 pi squared dx. I'll split that up and bring 1/2 over the bracket, so I'll get 1 over 2 pi sigma squared integral minus infinity to infinity x e to the minus x minus mu squared over 2 sigma squared dx is equal to mu outside of 1 over 2 pi sigma squared e to the minus mu over sigma squared dx, like so. And that thing, of course, given that p of x is equal to 1 over the square root of 2 pi sigma squared e to the minus mu minus sigma squared over 2, minus mu squared over 2 sigma squared, that thing there, recall CF, oops. So given that, this thing here is the expected value of x, this thing here, as we saw before, is just 1, and so if you put all of that together, we get the expected value of x is equal to mu, as we'd expected from the notation. So there it is. We have this probability distribution. Let me just write it down once more. It's p of x is equal to 1 over the square root of 2 pi sigma squared e to the minus x minus mu squared over 2 sigma squared. It's a probability distribution. Random variables that follow that probability distribution are called Gaussian, and the probability distribution has mean mu, and it has variance. We have improved this, sigma squared. If you take the expression for mu and differentiate it by mu again, you'll find out that the variance is indeed sigma squared. So that's fine, but what happens if we actually want to work out one of these probabilities? And there the situation gets a little bit complicated, because if the probability, well, say we wanted the probability that x is an element of x1 to x2. Well, I mean, this is a probability density, so that's going to be 1 over the square root of 2 pi sigma squared, x1 to x2, e to the minus x minus mu squared over 2 sigma squared dx. And so to work out this probability, we have to do this integral. Now, you might think that that's going to be easy, because I already worked out, or I told you it was possible, using what I refer to as an elegant trick, to work out the integral from minus infinity to infinity. And it might seem logical that if you can work out the integral from minus infinity to infinity, you could work out these integrals over smaller subintervals. In fact, the trick that allowed you to integrate from to work out this integral to show that this object was equal to 1, the trick I didn't show you, that trick relies on the fact it is an integral from minus infinity to infinity, and it doesn't allow you to do any of these other intermediate integrals. In other words, although we know this, we have no closed form formula for that. Now, you might wonder what I mean by closed form. What I mean is that we don't have a way of writing that integral in terms of the functions we already know. And that's a funny process. I mean, what are the functions we already know? What are sine and cos? Sine and cos we think of as being normal functions, but the reason we have a name for them is because they're useful, and we can't write them in terms of other functions that we already know. So in mathematics, you come up with these what people call special functions that serve some nice purpose, and then either you can write them in terms of the function you've already defined, or you give them a name and you make a table for them, and you call that a new special function. Now, a lot of the special functions satisfy nice differential equations. The sine and cos and the exponential and the log, all have definitions in terms of differential equations. The function that we're about to define, the so-called error function, is not quite so nice. It's not defined in terms of a differential equation, but it's defined in terms of an integral. So the idea behind this special function, the so-called error function, is that it allows us to perform integrals like the integral that we need here in order to work out this probability distribution. So what we want to do is we're going to take on board the idea that we can't solve this differential equation. We can't do this integral, but instead we're going to have a standard form of that integral, which we can work out or could work out tables for, and then we're going to relate the integral, this integral that we can't do, to that integral. So the special integral is called the error function. Erf of x, and erf of x is given by the integral 1 over the square root of pi minus x to x e to the minus y squared dy. So this, as I said, we can't do that integral, we can't do this integral, but this is kind of in a standard form. It's actually convenient to note that it's symmetric. So it's also the same as 2 times, well, if you go, instead of going from minus infinity to infinity, the bit from minus x to x, the bit from minus x to 0 is the same as the bit from 0 to x. So you can just write this as 2 over the square root of pi, the integral from 0 to x of e to the minus y squared dy. So this is the so-called error function. It looks like this. So as x when x equals 0, obviously you're integrating from 0 to 0, so you get the value 0. And then as x goes to infinity, it goes up towards 1. So it looks like this. And if x goes to minus infinity, it goes down towards minus 1. Now, again, the same technique that allows you to prove that this thing is equal to 1 if you go from minus infinity to infinity shows the error function goes to 1 as x goes to infinity, or goes to minus 1 as x goes to minus infinity. So this is the error function. As I said, it's a so-called special function in the sense that we're not going to relate this to other simpler functions. Rather, we're going to use this as the name of that integral, and if we can work out numerical values, using a computer, and there are tables. I mean, in the old days there was tables where you'd look up for different values of x what the corresponding error function is, that somebody had worked out using, I don't know, a slide rule or Napier's bones or some old-fashioned calculating device. These days, of course, your computer will be able to work out the error function. If you use, the math library, it will, on whatever programming language you want to use, it will have the error function. In some, mathematically aware programming languages like Julia, the error function will already be there. In others, you have to load a library, but it's been worked out numerically. So now, how do we do this integral? So say we wanted to work out the probability that x lies between x1 and x2. So again, I'll just write it again. We want x between x1 and x2. That's equal to this 1 over the square root of 2 pi sigma squared x1 to x2 e to the minus x minus mu squared over 2 sigma squared dx. Well, what we do is we do a change of variables. So we work with instead z, which is equal to x minus mu over the square root of 2 times pi. And if you do that, then dz will be equal to dx over the square root of 2 times sigma. So what I'm going to do is I'm going to do this integral by doing a change of variable. And the idea of the change of variable is to make this integral look more like that one. So let's do that. So I'm going to have to copy some things out, unfortunately. So I have the integral I'm interested in, p x an element of x1 to x2 is equal to 1 over square root of 2 pi sigma squared, integral from x1 to x2 of e to the minus x minus mu squared over 2 sigma squared dx. And so z, I said, was equal to x minus mu over the square root of 2 times sigma. So that's basically the square root of that thing. So we get e to the minus z squared. So that's good. The dx was equal to, well, we had dz is equal to dx over the square root of 2 times sigma. So we have one of those there. So we're just left with the 1 over the square root of pi dz. So in other words, the 2 sigma, square root of 2 sigma here. It's nice to write this as 2 pi sigma squared all inside the square root, but of course it's equally, it's the square root of 2 pi multiplied by sigma. So that is absorbed into the change of variables as well. And now x1 and x2, well, let's say z1 is the value of z when x is equal to x1, and z2 is the value of z when x is equal to z2 is the value of z when x is equal to x2. Well, then this goes from z1 to z2 like that. And so what we've done is we have made the integral just through a straightforward change of variables into a standard form, which makes it look a lot like the error function, and we'll complete that process now. So as I said, we can't do that integral, but what we're going to do is to relate it to a standard form of the integral for which tables can be pre-compiled. And so where have we got to? We've got to probability of x being in x1 to x2, given that, after this messing, this corresponds to the integral from z1 to z2, where z1 and z2 are known functions of x1 and x2, and so we get that. And so let's just write this now as 1 over the root of pi by the integral from z1 to 0 of e to the minus z squared dz, plus 1 over the root of pi the integral from 0 to z2 of e to the minus z squared dz, which is equal to 1 over pi minus the integral from 0 to z1 of e to the minus z squared dz, plus 1 over the square root of pi 0 to z2 e to the minus z squared dz. And so this thing is equal to a half the error function for z2, and this thing is equal to minus a half of the error function for z1, where, to remind you, the error function of any variable of z is equal to the integral from 0 to z of e to the minus y squared dy, or whatever it is you want to call the integrand. And so we've now related the original integral to the error function. So we get that p, the probability that x lies in the interval x1 to x2, is equal to a half the error function of z2 minus the error function of z1. And so if you want to work out the probability of x lying in these values, you just have to work out the corresponding values of z and then plug them into the error function, or in an exam you probably won't be asked to actually give the numerical values, just to relate it to the error function on the basis that if you had your calculator or tables or computer with you, you could then convert the z's into numerical values using the error function. So let's do an example of that quickly. Okay, so imagine a question where you're told the speed of cars on a motorway say they have average speed 90 kilometers an hour. So this is their average speed, and the deviation for that sigma is 10 kilometers per hour. So that tells you where the peak is, and it tells you something about the width of the peak. And what you're asked is, what's the fraction of cars that are traveling faster than 100 kilometers an hour? So what's the probability that x is greater than 100? Well, we need to work out our z's. So z is equal to x minus 90 over the root 2 times sigma, where sigma is 10. And we're interested in the cars that are traveling faster than 100. So z2 in this case will be in infinity, and z1 will be equal to 100 minus 90 over the square root of 2 times 10, which will be just 1 over the square root of 2. And here we know that this is equal to half the error function at infinity minus the error function at this value z1, which would be 1 over the square root of 2. And the error function at infinity we were told was 1, and since this will be equal to half 1 minus the error function of 1 over the root of 2. And that's the answer. And if you needed a numerical answer, of course you could plug that into your calculator or computer, and that would tell you the value.